Hey everyone, on the very beginning, I would like to thank Mateusz for the possibility to briefly talk about my work, which is also a big part of my personal interests, especially on ghosts, which is my favorite in the portfolio of Polish machine learning related conferences. I am Mateusz and I am a part of data science team in Pearson's AI learning capabilities. I work a lot on natural language processing domain. That's why today I would like to introduce you to semantic information extraction. AI learning capabilities is a part of the Pearson company. My team is responsible for the delivery of AI solutions that drive Pearson's products and applications. Pearson is based in UK, but my team is located in Poland. Most of us are from Poznań. In Pearson, we develop web and mobile platforms that help people around the world to learn English language. While learning English, you train skills such as grammar, vocabulary, pronunciation, but there are also other aspects which help to communicate properly. Comprehension, structure, discourse, and coherence, for example. And semantic information is a core of those that are related to communication. A lot of activities that you will take as an English learner are based on understanding and transferring knowledge. To give one example, I will use a task type that is called describe a graph. In such a task, learner has to analyze a graph and describe its content in a short response. If we want to automatically score that responses, we need to ensure that our systems understand English language. Sometimes we need to infer very detailed information. I have another example for that. Let's suppose that we have a short story, which is, yesterday I went with my sister to our local cinema. We bought a lot of popcorn and nachos. We wanted to see the next part of our favorite fantasy film. Unfortunately, at the beginning of the seance, a very loud fire alarm went off and everybody was forced to leave the cinema. As it turned out, the alarm sounded because someone was smoking a cigarette in the toilet. Now we will answer some questions. Does this text mention a situation in a cinema? Yes, it does. I have also bolded the parts that are answering those questions. So here, I went with my sister to our local cinema. The next question, does the storyteller have siblings? Yes, she or he has, because there is a mention about sister. Does the storyteller like fantasy films? Yes, she or he does, because there is a mention of favorite fantasy film. Does the story have a happy ending? No, it hasn't, because everybody was forced to leave the cinema. Does the cinema sell cigarettes? We don't know. There is no such information in this short phrase. Can a machine answer those questions? Yes, it can. Furthermore, you are able to do it on your personal computer even without GPU. Today, I want to give you some hints how to do that. So on the beginning, I would like to mention areas that our Pearson's NLP team work on, which are semantic relatedness, semantic similarity, and natural language inference. Those presented here, those three, are generally pretty similar. The biggest difference between is in how the training is done, if the method is supervised or not, or how the output layer of a model looks like. The most important fact is that their use cases are different. That's why I decided to talk about them individually. The very first we are going to talk about is semantic relatedness. I'm pretty sure that you already know it because this is basically a topic modeling. We can model topics using latent semantic analysis, LSA. Having a set of documents, which can be single sentences or longer paragraphs, you need to convert those documents into vectors using TF-IDF. Then you stack those vectors in a single matrix and conduct singular value decomposition. I am not going into the details of those methods. I believe that you heard about that something. SVD operation yields three matrices, U, S, and V. S matrix contains singular values on its diagonal, which are perceived as a topics, and I will tell you about those topics more soon. So to conclude, initial matrix simply stores information how documents are dependent on terms, and by term I mean words. After the decomposition, matrix U represent how documents depend on topics, and matrix V represent how terms depend on the topics. Why do we name them as a topics? It's because you can subjectively find some patterns in a given dimensions of the U and V matrices. If the documents are, for example, movie descriptions, then in all documents that are in fact science fiction movies, for example, we may be able to see high values on one given dimension. It is assumed that this dimension reflects science fiction topic. And of course, this is purely subjective, so you have to guess what dimension, which dimension represents which topic. As you can see, thanks to the LSA method, we are able to extract meaningful word and sentence vectors. If we treat document as a sentence, of course. Why do we name it as a semantic relatedness? It is because the vectors extracted with LSA can be similar even though they do not reflect the same things. Like is this example on the very top of that current slide. You can see that car and driver aren't the same things. Anyway, they belong to the same topics because they lie in the same documents, because this is very probable that having a car in a given document, there will be also driver. They are related, therefore their vectors will be similar because it was measured with LSA and SVD. Our conclusion is a good transition to semantic similarity, in which we want to produce vector embeddings that are similar for synonyms or paraphrases, not for entities that are only related to themselves. Examples for similarity embeddings. There are a lot generally. I have put here only the most typical examples like word-to-vec, BERT, like BERT token embeddings, BERT's contextual embeddings, which are on the very end, on the output of BERT. And some of them are polysemy agnostic, like word-to-vec, because for word that has, like, for example, 5 different meanings, you have only one embedding vector. While if you have the same word but in different contexts, on the output of BERT, we will have contextual embeddings, which are different because of the different contexts on the input. Why those methods reflect similarity instead of relatedness? It is because the particular word vectors are created with methods that check for word fitness within a given neighborhood of other words that are adjacent to a given word. In the case of word2vec, those methods can be continuous bank of words or skipgram. Thanks to that, embedding vector for a car will be more similar to word automobile instead of word driver, as it was in the example of semantic relatedness. You can easily substitute car with automobile in a sentence. I drive my car every day. You can say, I drive my automobile every day. But it won't be so easy to create meaningful sentence with I drive my driver every day. That's the reason why driver and car won't have very similar embeddings. Semantic similarity stores a lot of information related to parts of speech and word dependencies, and that's great thing about semantic similarity. To conclude, relatedness is more like having family, while similarity is like having best friends, in my opinion. You may ask now how to construct similarity embeddings for the whole sentences or paragraphs. To do that, we can, for example, calculate an average vector out of words that belong to the same sentence. So having a sentence, Michael was too tired to tidy his room. We tokenized it. So we have tokens, then we convert tokens to vectors. Then we add the vectors. And finally, we divide the result vector by number of tokens. Thanks to that, we received an embedding of the sentence. Of course, there are other methods to extract sentence embeddings. If you use BERT, one option is to use CLS output token, which stands for classification. Originally, this token is used to predict if input sentences are taken from the same piece of text. In other words, if the second sentence that was passed as an input to the model follows the first sentence. Such a process is done during BERT pre-training, and this process is called next sentence prediction, because you check if the second sentence is the next sentence after the first one. Therefore, you can use this output token to describe the whole input that was passed to the BERT. We can compare sentences the same way as we compare words, calculating cosine similarity between sentence embeddings. The use cases for that can be semantic search. Let's suppose that you want to find relevant content for your query. You are searching for a question, and browser automatically shows you the most similar questions that were already asked. Super useful, for example, on Stack Overflow. In Pearson, we may like to check if a student's response is on topic. For both of those cases, I use the term paraphrase detection. Of course, paraphrase detection can be applied to many more methods, but this one that I present is just one example. However, if you look for the most powerful sentence embeddings, be sure that you have checked sentence BERT. This concept is based on network made of two Siamese BERTs. So having a language model, BERT, for example, and a pair of sentences that are paraphrases, sentence A and B means the same. By feeding the sentences both to the same model with the same parameters, we want to achieve maximum possible value of cosine similarity between embeddings of those sentences. And that's how loss is minimized. So paraphrase detection seems to be powerful, but in practice, it's not enough. Let's suppose that we want to compare two sentences. The film, the first sentence is, the film received better ratings in Poland than in Germany. The second sentence is, the film received better ratings in Germany than in Poland. Let's suppose that we use the method that computes sentence vectors by averaging embeddings of all words that are part of the sentence. Those two have completely opposite meaning, but they have exactly the same embeddings because they have the same words in both sentences. So they lie exactly in the same point of vector space. How to overcome this problem? One solution is based on supervised learning, which means that we need to have labeled data. The good news is that such a data exists already and is open sourced. The data set which we can use is called multi-genre natural language inference, MNLI. It consists of 433,000 of data rows that are human labeled. Every data row consists of a premise, a hypothesis, and a label. We have three labels that are negative, neutral, and positive, and those labels are named contradiction, neutral, entailment. To give one example, hypothesis, the film received better ratings in Germany than in Poland, is a contradiction to premise that the film received better ratings in Poland than in Germany. And I can show you some examples right now. This is some kind of a demo that we use in our company to show how paraphrase detection and how NLI works, especially for people that have no idea about that, some stakeholders, etc. So let's suppose that our premise is the film received better ratings in Poland than in Germany. Okay. And on the beginning, I will use this model response treats those two inputs as a paraphrases. So first we check for sentence for semantic similarity, and we want to change it that way. Let me check. The film received better ratings in Poland than in Germany. The film received better ratings in Germany than in Poland. Okay, and we can see that this is the score of semantic similarity. This is calculated using SentenceBird. So under the hood there is SentenceBird model. Yeah, and the score is 99%. So we can see that this is not the best option here. On the other hand, the second field here is NLI. And I will check the same sentence. Yeah, and here you can see that the match score is practically 0%. So in this case, NLI works while paraphrase detection doesn't. We can check it further. Like now I can change this word better to be opposite. So for example, the film received worse ratings in Germany than in Poland. Yeah, and we see that this score here changed. Yeah, so this is very nice. Like this score is entailment score. We can see that NLI model predicts that the film received better ratings in Poland than in Germany. Is entailment to the film received worse ratings in Germany than in Poland. So we have something like double negation, and it still works. I can also show you another example. I have prepared a short text from Wikipedia about Black Sabbath. Yeah, we can see that for those examples here, this doesn't really work. But we can put some facts like this text. Some facts. I mean, facts are hypotheses. This text is about music, which is the first one that we want to check. Yeah, it's high score. Okay. What else? This text is about England. This text is about Ozzy Osbourne. Yeah, still 60%, but now let's change the hypothesis a little bit, because this text isn't purely about Ozzy Osbourne. It's about Black Sabbath and about their albums, about changes in lineup, etc. So let's change it to this text mentions Ozzy Osbourne. Yeah, and we can see that now entailment score is very high. So you can see that you have to be very exact about hypotheses that you make to receive high scores on entailment. Okay, and back to the presentation. Going back to the very first example, I have annotated a hypothesis with corresponding labels. So here we can see that the happy ending hypothesis is a contradiction because the storyteller didn't manage to watch the movie, and we don't know if cinema sells cigarettes. There is no information about it, therefore it's neutral. Free label training on MNLI dataset is a perfect example of zero-shot learning. Zero-shot learning means that trained model is able to predict classes that are unknown. Here I have shown outputs of 2 neural networks. Let's suppose that we don't see the rest of the network. This is just the last layers. So the first one is both are softmax outputs. The first one has 10 neurons on the end, and the second one only 3. Normally, if you wanted to predict what is the topic that your text belongs to, you train a classifier similar as the one on the left. So you have the topics, 10 classes. Each class is a topic. In the natural language inference, you are independent on classes. Class name is another input to your model treated as a hypothesis. So this text is about animals. This text mentions industry. This text, etc. Given such hypothesis, network needs to infer if this is actually true, if this is entailment. That's how zero-shot learning works. And summary, I'm not sure if I have to go through all of that, because I'm sure that you remember that what are word embeddings. That's, of course, everyone knows. There is a difference between similarity and relatedness. Sentence embeddings are good to retrieve general domain of a phrase, but unable to infer its exact meaning. So we use natural language inference, which is a good method to retrieve detailed meaning of a phrase. But on the same time, it's strongly data dependent and requires heavy computations to train a model. And the last point, few shot and zero shot learning is the future of NLP. Yeah, like the GPT-3 paper is basically named that language models are few shot learners. So you can see how this evolved. Yeah, also some useful sources that where you can find basically all what I have mentioned today. Treat my talk as an inspiration and introduction to the depths of semantic analysis and NLP. On the very end, I would like to mention that my team is currently recruiting. We are looking for data scientists. Open positions are for interns and also for mid-senior level. Please take into account that this talk was recorded nearly 1 month before the date of actual conference. Therefore, our offer may change a little bit when you see me talking. For more information, please visit our website, aipearson.pl. Also, I highly encourage you to join our conferential virtual room where we can discuss more about the NLP stuff and about my team. Okay, so thank you. See you.
Thank you, Mateusz, for your presentation. I think that looking for solutions that can improve online learning are even more relevant in current times. The first question is, in what kind of tasks for English learners NLI could be used?
So I think that the one example I gave from the very beginning, describe an image, is probably the best example. So in our case, for every item, and by item I mean every different activity, every different task or image, we define something like key points that can be mentioned by the students, and generally English learning designers or content authors define those key points. We give them guidelines how to do that, how to prepare the best input for NLI model to get the best possible efficiency. Then having the items and the key points, which are metadata of that items, we use NLI to score students' responses, and we check how many of them were actually mentioned. Of course, there are issues, like, for example, what is the ideal threshold of entailment score? When do we want to treat a key point as a mentioned or not? So this issue generally is solved by fine-tuning the thresholds and the model to the data we gather. So without our internal data that we collect based on actual learners' responses, we are able to do that.
Mm-hmm. The second question from Alicia is, the data set of NLI has three labels: entailment, contradiction, and neutral. How is neutral reflected when you get entailment percentage? Is there any way to distinguish between a sentence that is partially true and a sentence we don't have any information about?
This is a very good question, and I wish we had asked that question. We had asked that question at the very beginning of our research. So to answer that correctly, to have some kind of intuition, what is the difference between neutral and entailment, you need to dig into the data set, into the MNLI, and manually check for samples, check how they are defined. One thing I can say about it is that generally partially true hypotheses are treated as a contradiction. So for example, if the text is about apples and I have a hypothesis. This text is about apples and oranges. It is partially true in theory, but in practice, MNLI model will give you output with high contradiction score.
Okay, I think that's all for the questions. Thank you very much for your presentation and answering our questions. Is there anything you'd like to add?
Thank you for the possibility to be here, and see you in the chat of conference. I will be present in all other sessions. I will be also present in our Pearson's virtual room that is available like every time when you want to visit us. So yeah, see you.
Thank you, Mateusz. See you.